Okay, welcome back. We're going to do a bit more of the periodic table now. Now, we've got the central part of the transition metals, but let's go both left a bit and also right a bit. So, here we go. Right then. Now, chromium forms a stable hexacarbonyl with 18 valence electrons. If we want to move one step to the left, we can get ourselves an unstable paramagnetic hexacarbonyl. The problem is, as you go to the left, it's harder and harder to pack enough ligands around a metal to actually give you all the required electrons to give you 18 valence electrons. And also, incidentally, we can have vanadium. Maximum oxidation state of vanadium is +5, the chromium is +6, the manganese +7, and the iron group is +8. So, we can add vanadium. Now, after we've added vanadium, we now need to consider what comes to the left of vanadium. And it so happens it's titanium. Titanium forms titanium tetrachloride, which is a simple molecule rather than an extended thing. Now, on the left hand side of titanium, you then have scandium, and now we're going to go down the blocks a little. Now, underneath titanium, you have zirconium, commonly used for a manner of wonderful things such as corrosion-resistant tubes for nuclear reactor parts. And then you have hafnium underneath it, which is also very corrosion-resistant, but it's also very good at a neutron-absorbing material. So it's used when you want a neutron-absorbing material that's very non-corrodible. Now, you've got hafnium here and zirconium here. Now, in here there are two elements there. Now, you have niobium here. Wrong symbol. It's Nb, not Ni. And underneath niobium, you then have tantalum. In other words, rare things that I've never actually used in my chemistry, but I'm sure there's some very interesting chemistry for it. Now, we have most of our transition block, but we now need to add a few more. We have yttrium here. The yttrium here is an interesting one, because if you form yttrium-90, it decays by radioactive decay of beta decay into zirconium-90. And the parent of yttrium-90 is strontium-90, which gives us the position of strontium in the periodic table. Now, we know that immediately above strontium comes calcium, so that gives us where calcium is, and immediately below strontium you have barium, so that then gives us barium, and one step to the right of barium you have lanthanum. So now we're getting even more bigger. Now, if you so happen to make cesium-137, that decays by a beta decay into barium-137M, which gives us the position of cesium as its beta decay. As we know where cesium is, we now know that you have rubidium here, and potassium will go here, and above potassium you won't have sodium, and then lithium. Now, immediately one step to the right of sodium you have magnesium. This has a diagonal relationship which makes it easy to remember to lithium. The two are very similar in a lot of their chemistry. And then immediately above magnesium you have beryllium. Beryllium, horrible little metal, but it has an interesting chemistry, and it has a diagonal relationship with aluminium, which then helps us place where aluminium is. Because aluminium is at the other side of the periodic table, right here. So we now have where aluminium is. Immediately above aluminium you have boron. Boron and aluminium are quite similar. Boron trifluoride and triphenylaluminium are both Lewis acids. Now, if you now go here, you get to where carbon is. Carbon hydride or methane is definitely not a Lewis acid. That is a molecule that has no lone pairs, and also it cannot accept any lone pairs. So that gives you carbon there. Next step down from carbon would be silicon. Silicon is a heavy analogue of carbon. The chemistry is quite different, but it's still a heavy analogue. The next one down from there is germanium, not geranium. And then next one down from there will be tin, and then lead down here. Now, it's important to remember between lead and mercury you get thallium, Tl, and here you have gallium, and there in the remaining spot you have a space for indium. So now we have part of the P block. Now if we continue the P block a little bit more, after carbon you can then go to nitrogen. Nitrogen hydride or ammonia has one lone pair, and it's here. You have a lone pair and a total of 3 sigma bonded hydrogens, which gives you 8 electrons around the central nitrogen. Then you go to water or oxygen, which has 2 lone pairs and 2 sigma bonded hydrogens. Again, that gives you 8 electrons around the central atom. And lastly, almost to finish things off, you have fluorine, and then finally neon. Neon is a noble gas. Almost all things in chemistry aspire to be like a noble gas. So here we have an important point here, the noble gas. Now, if we go to the heavy analogue of nitrogen, which has a diagonal relationship to carbon, we have the phosphorus. Going down from phosphorus, you then have arsenic, and then antimony, as used in plastics as a flame retardant, as the oxide, and then a little bit further down there you have bismuth, which is debated of whether it's the last stable isotope ever in terms of atomic number. Some people say it's stable, other people say it's not stable. It's all about what you consider stability to be. How long does the half-life have to be before it's stable? So, now, if you neutron irradiate bismuth, you can make a bismuth isotope with more neutrons that then beta decays to make polonium, which gives you the position of polonium. Now, next thing to note is you have sulfur. Sulfur is an interesting one. If you take sulfur 32 and neutron irradiate that, what happens is it absorbs a neutron and spits out a proton, so it then goes to phosphorus 32, which is an important radioisotope in biology. Now, let's go down the periodic table a little bit. If we now go down here to this one, which will be selenium, we can then move down to tellurium. If you neutron irradiate tellurium, it then beta decays into iodine, which fixes the position of iodine in the periodic table. Here. And then above iodine and beside selenium you have bromine, and beside the sulfur you have chlorine. Now, we're getting a bit more. Now, next door to the polonium you have the heaviest of the halogens, astatine. It's AT, not AS. AS is arsenic. Now, if we continue our periodic table, let's add the noble gases. After neon, you have argon, which is a heavier one. Argon, which is the most common of noble gases in our atmosphere. Then you get krypton, and then iodine 131's decay product by beta decay is xenon, which gives us the position of xenon. And it so happens that by alpha decay, polonium is formed from radon, which then gives us the position of radon. And then immediately above the neon we have helium, and right at the other side above the lithium we get the hydrogen. Now, we now have almost the whole of our periodic table. Now, please stay tuned, I'll come back later to do the rest of it. At least the rest of it I can do. See you later, bye.